given those nice simplifications we've just discussed, I'm going to propose now an alternate, much simpler analysis process. In this case, rather than building the entire table, we're going to first choose a representative operation to count, which we called our cost model. And then we're going to figure out the order of growth of the count of the representative operation by either making an exact count and then throwing all the pieces away, the pieces we don't need, or using our intuition or inspection to figure out the order of growth directly. Now that's only possible if you've done this a lot. And what we'll do in a moment is I'll give you an example of each. So to do this, we're actually going to redo our work from this entire lecture. Once more, this time we're going to look at dupe 1, and we're going to use this new process, and I'm not going to skip any steps. We're going to show all of our work instead of having formulas appear like magic from space. Okay, so our goal now, this is dupe 1, rewritten slightly to fit in the same space, but it's the same function. And my goal is to figure out its runtime. So first, I'm going to pick a representative operation. Now there are many possible choices, but the one I'm going to choose is equal equals. Why? Well, because I happen to know that it lends itself to the easiest explanation. Now you might pick the wrong choice at first, and it comes with practice to feel like what seems like the most important part. But this is the choice I'm going to make. Okay. So, given that I picked the number of equal equals operations, the question is, how do you count them? So this will be the approach where I figure out the exact count and throw away the pieces I don't need. And so to do this, I'm going to use a nice little picture. And I love these pictures. Okay. So especially with nested loops, this is, and actually in all kinds of situations, these type of pictures are just gold for understanding. So this picture shows for which I and j pairs equal equals occur. So there's two ways to interpret this. Okay, and I'm showing the example for n equals 6. One is, well, which elements get compared? Well, elements 0 and 1 get compared, 0 and 2 get compared, 0 and 3 get compared, 0 and 4 get compared, and so forth. Or the alternate interpretation is just to look at the code and say which occur. So if I is 0, j will be 1, 2, 3, 4, 5. When I is 1, j starts at 2, right? And then it goes 3, 4, 5. When I is 2, or sorry, when I is 2, then j gets initialized to 3, and it goes 4, 5, and so forth. So all of these cases here, marked in blue with these equal signs, are when we actually run equal equals. And in the worst case, all of them occur. So what is the number of operations in this case for equal equals? Well, it's going to be 1 plus 2 plus 3 plus 4 plus 5, which is 15. But more generally, it's going to be 1 plus 2 plus 3, all the way up to n minus 1. So when n is 6, it's 5. But in general, it'll be up to n minus 1. Now, what is this? How do we solve this as a function of n? Well, you've seen this probably at some point in the past in math. But there's a nice little trick. I mean, there's just a formula for it, but there's a nice little trick here to figure out the sum of the first n minus 1 natural numbers. And that is, okay, well, we can, of course, write it the other way. N minus 1 plus n minus 2 plus n minus 3 all the way down to 1. This statement is surely true if this top statement is true. So if the count can be written this way or this way, we can actually sum these two equations and get 2c, like c plus c is 2c, is equal to n plus dot 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 plus n. Why this? Well, this first n is 1 plus n minus 1, which is clearly n. The next n is 2 plus n minus 2. The next one will be 3 plus n minus 3, and so forth, all the way to the n. And so we end up with an expression which is n plus dot 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 plus n. Now, if we count the number of these n terms, they're of course n minus 1. 1, 2, 3, da, 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 up to n minus 1. Okay, so given that there are n minus 1 of these n's, we can then say, okay, we could solve for c by simply saying 2c is going to be n times n minus 1, because there's n minus 1 n's. And at that point, we just divide the right-hand side by 2, and we end up with c is equal to n times n minus 1 over 2. Now, I blazed right through that piece of math because I'm assuming you've seen something pretty similar in the past. If you haven't, go check it out online. I'm sure there are plenty of cool demos going through this in more detail, but it's a old and common math trick, and in a future lecture, I think the next one, I'll talk about the sums that you really ought to know. Okay. So basically, though, in the end, what we ended up with is that the number of equals operations is going to be n times n minus 1 over 2. Now, given that we have the exact count for the number of equal equals operations, we could say, okay, what this operation equal equals, what's its worst case order of growth? Well, we throw away the lower order term, and we throw away the multiplicative constant, and we get n squared. The number of equal equals operations grows quadratically. And since equal equals takes constant time, and it's our representative operation, that means the overall order of growth of the runtime is n squared. And that's the entire analysis. You'll notice we did not have to build a giant table. We had to do a little bit of math, but it wasn't so bad. Now there's an alternate way where we don't actually come up with the exact count at all. Now this is more of an art than a science often. And in this case, I'm going to make a geometric argument. And eventually, once you get really good at this, you can start doing this, but it is a trickier technique. So in this approach, again, I'm going to count the number of equal equals operations. However, rather than counting the exact number, I'm just going to observe that it grows exactly like the area of a right triangle of side length n minus 1. So this right triangle here has side length n minus 1. And so the order of growth of the area as a function of n is clearly going to be n squared, right? You don't even need to remember the area of a triangle formula. You just have to realize that as you expand this box, that the area of half of the box is going to grow like the square of the size of the universe, which is also the side length of the triangle. That's it. Now I know that's a more subtle argument, but it's a beautiful argument. And this kind of thing is actually very common in algorithmic analysis when you want to really bring it to the next level, where you don't want to waste your time with all these summations. Instead, you rely on geometric reasoning. So in this case, we say that the operation equal equals, which is our representative operation, the order of growth of the number of equal equals is n squared. And since equal equals takes constant time, the order of growth of the runtime of the entire function is n squared. All right, so that's just an alternate way of deriving it. Now, all of that said, right, this lecture actually, it's a lot of doing the same thing over and over, you might have noticed. But ultimately, right, the reason I went through building the whole big table is to put us on a firmer foundation so that when I give you an argument like this, you could feel a little better that it's going to work. So the last thing we're going to do in this lecture is get a little bit more formal, and I'll discuss that in the next video, but this right here is the core of it. This is what algorithmic analysis is like, and you have to get lots of practice before you can really feel confident about it, but we'll have plenty of homework questions for you to try out and build your skill with this tricky analysis technique.